this episode we're going to talk about spectra and Max Planck. So let's talk about this cool phenomenon called emission. So what happens when an electron is in an energy level and wants to move to another energy level, it can absorb a photon of light, which gives it enough energy to jump to what is called the excited state, which is a higher energy state. So it jumps to another orbital. And this happens through a process called absorption, where the photon is absorbed by the electron, and it is reverted through a process called emission, where it moves down an energy level to its resting state or lower energy state or preferred state by emitting the photon. And the cool thing is we can see that there are distinct energy levels by looking at the photon emitted by these electrons when they return from their excited states. And this is unique for each element, and this is called its emission spectrum. Over here we have the hydrogen emission spectrum, and you can see these specific lines are when the photon is emitted. And Max Planck figured out that E equals hf through his constant, where f is the frequency of light or the photon emitted. And that proves that the energy, based on whatever color or whatever frequency of the light spectrum is emitted, is at a specific place. So, as you may or may not know already, red is a higher wavelength, greater wavelength, lower frequency, and lower energy. This E equals hf formula can also be translated into E equals hc lambda, and this is the value of h in meters squared kg per second. And as I said, every different element has its own unique emission spectrum. It's incredibly useful in identifying elements, especially when you get to astronomy, where you want to find the kinds of elements in a star. You use these emission spectra. And usually light is emitted or randomly in a continuous spectrum. But this distinction through a line spectrum states the fact that there are specific energy levels at which these electrons can exist inside the atom. But the cool thing is that at a certain point, when the electron is moved far enough away from the nucleus, it goes, say, here, where it is out of the reach, its ionization energy. And that happens at a super high frequency. Basically, the emission side, when it comes from outside into the inside, it emits a photon at a really high frequency. And that is the ionization energy. That E equals hf, which we solve for, is the ionization energy. And what happens is at higher energy levels, it converges into a continuous spectrum, because after that it's like infinite energy. It's any amount of energy greater than that, any frequency greater than that, will result in the electron being released or gotten back. And that is after the, so exactly where it converges happens to be the first ionization energy. Cool. So let's look at an example. So the ionization energy of mercury, Hg, is about 1.67 times 10 to the negative 18th joules. And I want to know at what wavelength it converges. And I'm going to suggest you to pause the video and try figuring it out using the formulas we had above. And I'll present the solution in just a bit. So the answer I got was, it was 1.19 e to the negative 7th meters. That is something like 119 nanometers, which is in the X-ray region, which is pretty high energy. So yeah, cool to know.